Well, thank you very much for the invitation to speak here today. I wasn't expected to use this beautiful auditorium. And thank you, John, for the invitation. And welcome for all of you that are just arriving to Princeton. And today I want to talk to you about this problem we've been working with Benoit Bertrand and Erwan Brugale about find topological bounds for tropical varieties. For tropical variety, I mean polyhedral complex that are balanced in the sense of the combinatorial definition. And for the first example, I want to show you this. This is a tropical curve of degree 3. Every tropical variety has a degree, a dimension, a codimension. Here we have a planar cubic tropical curve. And we can see, I don't know, that we have a genus 2 curve. Genus 2 means we have these two holes in this picture. And this was constructed in 2017, and it was published in 2017. And before that, we thought this curve didn't exist. And the reason why is because in classical algebraic geometry, every cubic curve in any dimension has at most genus 1. Then this was the first example of something that goes beyond the bounds known for the algebraic varieties. Okay, then we want to study this kind of questions. For example, we want to bound the maximum of the Betti numbers of a variety of dimension d of a given degree, given dimension, given codimension, where the Betti numbers are the dimension of the homology group, and we want to bound these numbers. And the difference between the algebraic case and the classical algebraic case and the tropical case is that these bounds in the tropical case depends on the codimension. In the algebraic case, they don't depend on the codimension, and the reason why is because if I have an algebraic variety, I have a whole projective space of direction where we can project, and we can always project in a direction where these numbers didn't decrease. Then if we know that this is true for hypersurfaces, then we know that we have the same, the codimension didn't affect these bounds. Okay, this is the numbers we want to study is given D, M, and N. We want to study the supreme of the Betti numbers of the all tropical subvarieties of dimension M, degree D, in the projective tropical space of dimension N. For example, here we have again a cubic curve where we have the zero Betti number is 1 because it's connected, and the first Betti number is 1 because we have genus 1. If anybody doesn't know about Betti number, just think about it as a generalization of the genus, for example, because we're going to study mainly the top Betti numbers. Okay, then we want bounds for these numbers. For example, once we see these numbers, we see that we can construct a planar tropical cubic of any genus G. Like we cannot only construct a tropical cubic with genus 2, we can construct a tropical cubic with any genus. We just have to go to the right codimension. Plane, yeah, right. Yeah, I mean it's contained in a two-dimensional plane, and it's like a hypersurface in this plane.
By two-dimensional plane, you mean?
Tropical plane. Sure. Otherwise, it's not true. Okay, here we have again this very first example. It's the very first example because it's dimension 1, and it's the first time we have something that is not genus 0. Okay, then let's recall the classical case. Then we're going to see some bounds for the tropical curves for higher dimension, and if we have the time, we're going to see the proof that are mainly constructive. Then we're going to draw the example. Okay, then in the very first example of a planar of a tropical curve that wasn't the limit of amoebas of algebraic varieties was this example by Mikhalkin that was a tropical, again, we're again with the cubics, was a tropical cubic of genus 1 that wasn't planar in the sense of didn't belong in a tropical plane. And this example was constructed in around 2008 or around. And I think we didn't realize that what was happening, that we were going beyond the tropical bounds of the algebra. I mean, we realized it, but we were so surprised, mathematicians were so surprised about the fact that find a non-realizable tropical curve that we didn't go in the direction of try to construct more examples of tropical varieties that doesn't have the same bounds. And the reason that is obstruction is because any non-planar complex cubic has genus 0. Then it can be the limit of an amoeba of a cubic, of a complex cubic, because it has genus 1. Okay, for the curves, we know very well the case of curves. The genus of a curve of degree C, complex curve of degree C, it's at most d minus 1, d minus 2 over 2. And we're going to call this B1C of D. And this number don't depend on n. Means doesn't depend on the codimension. And has a very nice combinatorial picture that is the number of interior points in a simplex. Then, for example, for cubics, we have that the complex cubic has at most genus 1 is because in this triangle we have only one integer interior point. And for quartics, we have that the genus is at most 3 because in this triangle we have 3 integer points. Then all these numbers are simplicial numbers, triangular numbers. And for higher dimension, sorry, we have that that is exactly the same. We have this number that is again we can see it as the number of interior points of the n plus 1 dimensional simplex with vertices in the origin and d times the standard base. Then these are the bounds. They are sharp and doesn't depend on the codimension. Okay, and now we want to see what happened between the tropical case and the algebraic case. We know known cases is for dimension m, dimension 0. Sorry, we have that the number of points in a 0-dimensional tropical variety is exactly the same as the complex case is d. And for dimension bigger, positive, strictly positive, we have that in the case of hypersurface, we are in the case of dimension m in a space of dimension m plus 1, and we are in hypersurfaces. Then we have that the 0 Betti number is 1. Between 1 and m minus 1, the Betti number is 0. And the top Betti number is again the same of the complex one, and it's because of the duality with the composition of the simplex of dimension n+1. For the tropical things, Juju proved in 2014 that this number is finite, and we extend it to any dimension, then we know that this number is finite. And what we proved in 2017 is that if we have sorry. If we want to bound the top Betti number of degree d dimension m in TPN, then we have this at least the codimensions times the complex bound. That, for example, works very well in the case of hypersurface because the codimension is 1, and then we have equality there. And how we prove it is by construction. We construct varieties with exactly these Betti numbers. And if I have time, I'm going to show you the construction later. I don't know what time is it. And we can see that since it depends on the codimension, if we make the ambient space tends to infinity, we're going to see that these numbers are tends to infinity too. Then we really can have Betti numbers as large as we want. We only need to be in the right dimensional space. Okay, then what we prove is that given 3 positive integers, there exists a tropical variety X of the given dimension degree and in TPN with exactly this, the top Betti number. And it's contained in it's again contained in a linear space, tropical linear space of dimension n+1, where it's like a hypersurface in this sublinear space. In particular, as we have seen, for any integer n greater than 2 and k at least n-1, there exists a planar genus k tropical cubic cube in TPN.
This thing for the plane that contains these curves,
Mm-hmm.
do you have to choose the rank matrix carefully, or is it just following something?
Sorry?
The plane that contains this curve, do you have to choose it carefully?
I mean, in the construction, we made it like by modification of a plane, a regular plane, and then we have to choose the modification. Mm-hmm. I mean, it's a construction. Once we're constructing the curve, we're at the same time constructing the. Yeah. Very well. I was sure someone is going to ask this. You can think as in the case of algebraic varieties, you can intersect with a complementary dimension linear space and count the number of points. And in the case of curves, for example, we can have a very nice definition, general definition, that if you have a non-bounded rays in the standard directions, and the sum of the weights are of this degree. Here, for example, we have 3 rays on unbounded rays in the 4 standard directions, and this is all of them of weight 1. Then this is a tropical cubic. Okay. In the unbounded. Otherwise, I'm sorry, I forgot to in this edge that passes to the vertex, the weight is 3.
just with one, or will you have
Yes.
this for all weight combinations for the other?
You can choose. It's you can choose how the unbounded race doesn't. I mean, we make this just to be sure that we have all this, the more non-singular. In fact, I didn't wanted to go in this direction, but once we're there, I told this is an edge of weight 3. It means it's a singular tropical curve, and with a slight modification of the construction, we were able to construct a genus to non-singular tropical curve. I mean, we can forget the weight 3. Then, and we can have we see it for cubics, but we have the same result with the same construction for any degree. It's degree D curves in TPN, and we have again that the codimension is n-1 times the complex bounds. And in the case of dimension M, we have exactly the same result. It's the codimensions times the complex bound. This is the construction we have. And obviously, we want to know if this construction is sharp or is not sharp. And we don't know. In general, it's an open question. We have this construction. In the moment we go out of the algebraic world, we don't have many tools to work with. Then it's really like a puzzle. Or maybe you have tools, and I will be very happy if you have any idea. And we only have one case where we are sure that the construction is the maximal one is in the case of the cubic curves. It's the only case where we are sure that the genus of a tropical cubic curve in TPN is at most n-1. It's the smaller example. And it's the only one we were able to prove it, and I'm going to show you why we cannot generalize very well this proof. And it's because we want to prove that the result. We're again in this picture that is the main picture. Yes?
But the upper bound, can you say a word about how you prove that this numbers are fine?
It's again with the projections. I mean, the main difference between the algebraic case and the tropical case is the projection you can use. And even if you have in TPN, you have only n+1 linear directions to project. Then it's a finite number of projections. You don't have many directions. But even if it's not a linear one, you can always choose a projection that preserves all the genus. And if you, by induction, you suppose that in lower dimension is finite, you will always have this. But here we are projecting in non-linear space, non-linear directions. And this is the main point. The main point is in TPN, we only have n+1 linear directions to project. And we're going to call this projection P0 until Pn in direction E0 to En. And what is easy, well, easier, it was easy to work with the tropical cubics is that imagine you have a simple closed curve containing a tropical variety. Then if you project in this linear direction and it's a tree, we're going to say that it collapses in this direction. And we have a simple closed curve in a cubic curve in TPN. This simple closed curve will collapse in at most two linear tropical projections. Then it survives in many of the. And with this remark, this is not the case in general. We have, for example, this is the so-called Ricard's curve. That is this pink object, and we can see that there are three directions where the image is a tree. But to embed this object in a tropical curve, you need a degree, I think is between 10 and 20 or something like that. Once I calculated, but I don't remember. But we don't have this result in general that it collapses in at most two. Okay, then if it collapses in at most two, we have this. I want a pointer, but we have this inequality. The sum of the genus of all the projections will be n minus 1 because of if we are working in we go again, sorry. I'm going to project in all n plus 1 directions. I'm going to sum the genus of all the projections. And then we're going to have that all the sum of that is going to be more or equal, greater or equal than n minus 1 times the genus of C. And then if we want to make the proof by inductions, for n equal to 2, the result is well known, is the case of hypersurfaces. And we can suppose that it's true for n minus 1, that any cubic curve has a genus at most n minus 2. And then we can make again the sum of all the genus of the projections. And we're going to have n plus 1 projections, and all of them has at most genus n minus 1, then the sum is bounded by this number. And if we combine these two numbers, we can have that the genus of C is bounded by n minus 1. Then we're using the fact that the cubic curves, the genus of a cubic curve is exactly the number of simple closed curves contained in it. This is a very particular case of for cubics. And the fact that we have exactly n plus 1 projections. And this is a case where we know our construction is sharp. Then if any of you have any idea of go further in the dimension or in the degree, we will be very happy. I think one first step is go in the curves in general. And the other case is go in the case of, I'm going to say Calabi-Yau things, that it means of degree of dimension m and degree m plus 2. Because again, we're going to have this situation where the number of spheres embedded in we're going to be exactly the Betti number. I think this is the two easiest ways to try to generalize this. And for the case of curves, I wanted to use may I use the blackboard? For this, we're going to use for any n, we're going to use three curves to make the constructions. And I'm going to draw the Newton polytope of them. For the first one, we're going to, and this is what you were asking. In fact, here you will see that we are free in the first one. We want to have these 3 points. We are sure to have this polytope. But we were asked to don't have any of the points in this line. For the second one, we're going to have this, and we want this, all of the points here in the interior. We want all the points in the interior, and we don't have any point here, any point here. And for the third one, we don't have any point here and all the points here. The sides where I don't have the crosses is going to be related with the unbounded edges. Then here we can choose if we have one or, okay? Then we're going to pick this curve. This curve, I'm going to make it in the case of the cubic. Well, I'm going to make in general. I don't know what is happening here. I just know that the genus is maximal, and here we have an edge of weight D. The other one is, I don't know what is happening here, but here I have a dimension, degree D, weight D, and here I'm not sure. And the last one is something like that. Okay, and I'm going to take my scissors. I'm going to pick a point in this edges with weight D. And now I'm going to glue them. I'm going to pick the first one, and I'm going to choose that this point is going to be the origin. I'm going to embed it. These all three are in dimension 2, and I'm going to embed it in x3 equal to 0. Here is the point where I cut. And I'm going to glue to this one, where I'm going to embed it in the part of the tropical plane where x1 equals x2. And we can continue. We have this point. We can move our curve in terms that this is the origin. We can embed this in x4 equal to 0, and this one in the corresponding other face of the plane. And we're going to make all these movements. For any step, I'm going to take one copy of this one copy of this one, and n-3 copies of this one, and we're going to glue them, making a half turn in each movement. Okay? And then this is the construction. This is how we construct in the case of curves. Is this clear? Yes? And in your question, June, we are making modifications in a hyperplane with this center, in a standard hyperplane, linear hyperplane with this center. Then we are modifying not only the curve, but also the plane where we are working on. Okay, this is our construction for curves. And at the moment we were making this construction, we were a little bit perturbed by the fact that since the local dimension in the curves is 1, we were able to make this like turn. But in the case of in the higher dimensional, the dimension of the span of the curve is higher, then we couldn't do it. And then we develop a method that is called floor composition. And maybe you have heard about floor decomposition. And this is like opposite of the floor decomposition. Floor decomposition is a method used by, developed by Erwan Brugali and Grisha Mikhalkin to make computations of enumerative problems, and using this is now it's called floor diagrams. And the idea of the floor decomposition, let's go to the decomposition. A tropical curve is said to be floor decomposed. I'm going again with my cubics, sorry, where they are easy to draw. For example, this one is a floor decomposable curve in direction E3, because if I mark all the edges that are parallel to E3, we're going to have that this curve decompose in floors. That it means I have this floor that is a tropical birational curve, birational graph. This one is also a birational graph, and this one too. Then this is what is called a floor decomposable variety. And what we did is make the opposite. What means is I'm going to work by induction. We make the case of the curves. Then, well, I'm going to go down and go in dimension 0. Here we have a degree 3 tropical variety of dimension 0. Here we have a 2 and 1. I'm going to choose some planes and some one-dimensional lower varieties of degrees from the one we want to construct onto 1. And we're going to modify this plane, this line, with a birational tropical variety. And then we're going to have this, like, the modification is going to be like this. And then we're going to have, again, our scissors, and we're going to cut. And then we're going to take this one, and we're going to glue here. And then from dimension 0, I construct something that is of dimension 1. And then the genus, it will be the sum of the corresponding Betti numbers of the intermediary degrees. And it's exactly what happens in the case of the simplicial numbers. We have a degree 3 Newton polytope of a 0-dimensional variety. We take one of them of degree 2, one of degree 1, and then we're going to construct, using these floors, we're going to construct something that is with this genus. And then we can continue this procedure for once we have the curves, we can make exactly the same constructions and have surfaces, and the proof is like this. Then it wasn't easy. It wasn't this to find out how to go from the case of curves to higher dimension. It requires to develop of this method, but finally we did it. And for the moment, we want to know if these are sharp or not. And I don't know if you have questions, but in any case, this is what I wanted to say.
So if I understood correctly, you're using the floor composition as a kind of a constructive method to construct, no example. Floor decomposition usually, like you said, is used for enumerating all the possibilities of a situation. Is there a place where floor composition and floor decomposition meet?
In floor. No. But I wanted to say, because maybe some here knows about this floor decomposition or floor diagrams, and they came from this kind of constructions or deconstructions. Well, thank you.
Construction for two examples before here. And if you just stop immediately, you would get the one you showed us on the first slide.
Exactly. I mean, we're not going to use the one with two.
Yes, but the middle one.
Exactly, only that. Because n minus 3 is 0.
This is one way of getting tropical varieties that are not tropicalizations.
Yes. All of them are not topicalization because that's the whole point, that we don't have any algebraic tool there. And if you ask, I'm going to ask myself if I think they are sharp or not. What happened here is, if you see all the for example, all the cycles I'm going to construct in each step will collapse all in the same directions. Then the projection won't be maximal. Then maybe there's another way to make that, because in the case of curves, all the projection will be maximal. Then that's why everything works. But in this case, we have a lot of direction where everything collapses, because all of them are constructed with parallel phases. Then I'm not sure. I'm not sure if sometimes I think I mean, I found very beautiful that if the bound is codimensions times the complex bound, I think it's a beautiful bound, but I'm not sure if it's going to work or not.
Okay, if there are no more questions, let's thank Lucia once again.